Hi there, welcome back. This is week 3 of our course, Revolutionizing Construction, a comprehensive guide to 3D concrete printing. In this week, we are discussing about one essential part of the process, of the 3D concrete printing process, which is pump. So in the case of fused deposition modeling, or FDM, which is the classical plastic 3D printing method, similar to concrete 3D printing technology in the sense of layer deposition. The filament made of thermoplastics or thermostatic plastics are fed into the nozzle from a filament spool or reel. The material is then melted and deposited on the desired position and solidifies as it cools. 3D concrete printing is similar, but no thermal process is involved throughout the process. The material is fed into concrete pump, actually the hopper, the material container, and the material is pushed through the hose with the help of positive displacement mechanism and eventually extruded similar to ramp extrusion. Let's take a closer brief look into the flowing concrete while it's being transported. I'll give you an explanation about the types of concrete pump using in 3D concrete printing and some underlying mechanisms of concrete pumps. And later on, we're also going to look at what's really happening to the flowing concrete. Let's first browse through the different types of concrete pumps, focusing on the pumps for 3D concrete printing. The first and foremost common pump type for 3D printing is a rotor-stator pump, or also known as a progressive cavity pump. The name rotor and stator actually refers to a part of a pump normally connected to a hopper or material container. So this is the type of positive displacement pump used in various industries, including construction for pumping materials like mortar, slurries, or viscous fluids. It's comprised of two primary components, as the name implies, a helical rotor and a stationary helical stator. The rotor is a single helical-shaped steel or rubberized metal shaft that rotates within the stationary double helix-shaped stator. The rotor has a screw-like shape that fits snugly into the stator. The stator is a tube-like structure, typically made of rubber or elastomeric material that surrounds the rotor. It has a double helix internal shape that matches the rotor's helical profile, but with a marginally larger diameter. This creates a series of sealed cavities between the rotor and the stator. As the rotor rotates within the stator, it forms a series of sealed chambers or cavities between the helical shapes of the rotor and the stator. This design creates a progressing seal line that moves along the length of the pump as the rotor turns. The rotation of the rotor inside the stator generates a continuous positive displacement action. Each cavity created by the rotor stator interaction progress along the length of the pump, trapping and moving the fluid or material from inlet to the outlet. The trapped fluid or material is pushed along the pump by the rotating cavities, maintaining a consistent flow. The seal between the rotor and stator prevents a backflow, or also called a backlog, ensuring an even and controlled discharge of the material. Rotor-stator pumps are versatile and suitable for handling viscous, shear-sensitive, or abrasive materials. They are used in various industries, including construction, wastewater treatment, food processing, or oil and gas, for pumping materials ranging from a thin liquid to highly viscous substances like grout, slurries, paints, and adhesives. Rotor-stator pumps can handle high viscosity fluid efficiently, often achieving higher flow rates compared to other pump types handling similar materials, Also, these pumps typically produces less precision, so compared to some other pump types, resulting in a smoother flow. But it has a few drawbacks to concern at the same time. Their intricate design and component prone to wear and tear, which necessitates regular maintenance and periodic replacement, especially when dealing with abrasive substances, for instance, in our construction site, angular-shaped coarse aggregates. Additionally, their efficiency might diminish when handling materials with changing viscosities, properties, leading to challenging in maintaining consistent flow rates. Moreover, cleaning these pumps thoroughly after handling viscous or sticky materials can prove labor-intensive due to their complex design, posing practical challenges in certain industrial settings. Most of all, this type of pumps are often limited to a larger solid depending on the gap diameter between the rotor and stator, basically the specification of the rotor and the stator, the meaning constrained to use these pumps for a large aggregate contained concrete pump. So this is typically used for the mortar pumping or mortar 3D concrete printing. Another type of pump being used in 3D concrete printing is a piston pump. A piston pump is a mechanical device employed in the concrete pumping process utilizing a piston-driven mechanism to facilitate the movement of concrete mixture through a system. This actually comprises of essential components such as a cylinder and a piston, inlet and outlet valves, and a power source like an electric motor or a diesel engine. This system operates with the piston oscillating within the cylinder. During the retraction phase, a vacuum is created, prompting the inlet valve to open and allowing the concrete mixture to get into the cylinder. As the piston moves in the opposite directions, the inlet valve closes and the outlet valve opens, expelling or extracting the concrete the mixture. The cyclic motion of the piston ensures the consistent and controlled flow of concrete material through a pumping system. In many cases, the piston pump uses 2 or more cylinders hydraulic pistons to deliver extensively larger volume of concrete. The piston pumps are highly regarded for their reliability and precision in handling concrete mixtures with varying viscosities and pressures. They excel at generating high pressures with greater volume, making them well suited for concrete pumping applications that involves the transfer of mixture containing aggregates, which is the most advantageous part of using this pump because the previous pump is limited to use larger or coarse aggregates. In concrete pumping scenarios, these pumps prove advantageous for their ability to maintain a steady flow rate, ensuring a reliable and uniform delivery of concrete, especially through pipelines with diverse lengths and elevations. While piston pumps offer notable advantages in concrete pumping, it's essential to acknowledge that they demand regular maintenance due to the wear and tear associated with the repetitive movement. This is actually quite similar to the previous type of pump. Additionally, the complexity and the cost of these pumps may be higher compared to some alternative pumping mechanisms. The double feeding actions from 2-cylinder hydraulic piston pumps are not extruding the material continuously or smoothly, but making a pulsation flow. So there's like a stop and go, stop and go, stop and go. So it necessitates to be paired with end effector or another mixing system or mixing the station at the nozzle for smoother or continuous flow for the extrusion. I think I'm going to make a quick stop here before getting really deep into the detail of pump theory with the material, what's really actually happening into the material. Please stay awake and I will see you in a bit. So yeah, bye for now.